my pleasure to introduce Bruno Carvalho, who's giving one of the invited talks on carbon dioxide-bearing fluid inclusions in granulites. So let's take it away.
Thanks, Richard, and hi, everyone. Thank you for the invitation. Today, I'm going to show you some results of our research on the fate of fluids trapped in granulites. And as you will see, these results, they challenge some classic views for the evidence of fluids in high-grade rocks. But at the same time, we offer new insights to investigate their presence. So this work was done in collaboration with several people, and you can see them here at the bottom of this slide. So I will start with a basic background on fluid inclusions, then I will talk about the debate on fluid regime and the old perspectives of CO2 inclusions in granulites. Then in the second part, I will talk about the case study that we did. I will discuss the implications of these results before I leave you with a take-home message. So let's get started. What are fluid inclusions? So there are small droplets of a fluid that can be liquid, vapor, or a supercritical fluid that are encapsulated into rock-forming minerals. And an important genetic distinction is between primary and secondary inclusions. So primary, when the inclusions are trapped during the host formation. And in this case, we will see the inclusions forming isolated clusters or zonal arrangements, such as in the sketch here. Secondary inclusions, they are trapped after the host formation is complete, and as a result, we will see the inclusions forming planar arrangements in the crystals. Pseudo-secondary inclusions, they also show planar arrangements, but the timing of entrapment is relatively closer to the primary ones. And this mode of occurrences, they provide different petrological information. So fluid inclusion studies, they can be done using microthermometry, so by heating and freezing the inclusions to get melting and homogenization temperatures, but also with Raman spectroscopy. And specifically in this case, we can obtain not only the fluid phases, but also the solids if present inside these inclusions. And with both techniques, we can get the density of these inclusions, and more specifically with Raman spectroscopy, for the CO2, the distance between the Raman peaks, which are called fermidiad, this distance is correlated to the density of the inclusions. So the greater the distance, the higher the density of the inclusions. Here there's an example. So the density of inclusions, they can and they have been used to determine the PT conditions of entrapment of fluids. And this is done using isocores, which are lines of constant volume and density. And here there's a PT diagram with isocores for CO2. And as you can see, if we take this red line, which is the isocore for 1.1 gram per centimeter cubic, we can see that inclusions in CO2 inclusions that may be trapped at conditions of about 1,000 degrees and almost 9 kilobar, they have similar densities of inclusions trapped at about 250 degrees and 3 kilobar. So this means that it's paramount for us to be careful when we interpret the density of inclusions as an indication of high PT conditions of entrapment. Because as you just saw, high density inclusions, they may also be trapped at lower PT conditions. And as I will show you today, the density may be modified after entrapment. So we know that crustal melting and the ascent of anatectic melts towards their surface represent an efficient way to promote the chemical differentiation of the continental crust, and melting conditions and dynamics in the crust, they are deeply affected by the fluid regime. And yet, the roles that fluids may play in high temperature metamorphism and anatexis remain a debated topic. So on one side, there are works arguing for predominant fluid absent anatexis, and there are other works that consider fluids, either carbonic, aqueous, or brines, as essential agents in high temperature metamorphism and anatexis. So these works, they consider the presence of a fluid during the prograde path or at metamorphic peak conditions. And a classic example that may be quoted is the pioneering work of Touré. So here, one of the first papers that he published, where you can see the inclusions. He was working with granulite rocks from Norway, and he saw that the fluid phase during granulite metamorphism was composed almost exclusively of CO2. And another classic but controversial example are the incipient chinokites from India. So in this place, CO2 fluid has been interpreted to infiltrate a garnet biotite gneiss to form the dry assemblages of the chinokites. And additionally, there is an extensive literature about the presence of superdense monophase CO2 inclusions in granulites. However, the timing of entrapment of these inclusions sometimes remains controversial. And the majority of studies have investigated fluid inclusions in quartz because this host does not react with the fluid and is a ubiquitous phase in metamorphic rocks from all grades. However, inclusions in quartz, they may be incorporated at any stage of recrystallization, and some studies show that the composition can be modified by deformation and grain boundary migration. So this explains why there's much uncertainty about the timing of entrapment of inclusions found in granulites relative to metamorphic peak conditions. So the solution to this problem is to look for primary fluid inclusions in peritectic minerals. So these are the most reliable witness of fluids operating during deep crustal metamorphism, because the peritectic minerals, they are by definition the solid products of high temperature melting reactions. So in order to enlighten all those controversies on the timing of entrapment, in this study, we investigated inclusions in garnet from 3 metamorphic terrains where the garnet was formed as a result of incongruent melting reactions, and the inclusions are clearly primary in origin. And our main objective was to evaluate the fate of these fluid inclusions in high temperature and ultra high temperature metamorphic terrains. So the first occurrence was the Atabasca granulite. Here the macroscopic view of the rock we studied. It was a megmatitic paragneiss with garnet, limonite, kyanite, ternary feldspar, quartz, rare biotite, and plagioclase, but with abundant graphite together with other accessory phases. The PT conditions of formation, the temperatures are about 800 to 950 degrees. And as you can see here on the right side, the garnet in these rocks contain abundant inclusions on its cores, and this arrangement is clearly a primary arrangement of inclusions, meaning that they were trapped during the crystallization of the garnet. And when we look more closely into those clusters, we see that these inclusions, they are not only solid minerals, but there are also 2 types of multiphase fluid inclusions. Nanogranitoids, which are former melt inclusions. Here there are some examples. So these former melt inclusions, they are crystallized into a cryptocrystalline aggregate of granitic assemblage, here with plagioclase, K-feldspar, quartz, biotite, sometimes with rutile as well. And the fluid inclusions, they are multiphase. So in this case, the fluid phase has a CO2-rich composition with traces of methane and nitrogen, and the CO2 densities are variable and below what is expected for the PT conditions of entrapment. So with Raman maps and point analysis, we obtained that we observed that these inclusions are composed of magnesite, quartz, corundum, graphite, calcite, dolomite, and also the OH-bearing pyrophyllite. So we did a serial sectioning of these inclusions with the focused ion beam in order to reconstruct them in 3D. So here there's some of these, some of the sections that we did in one of those inclusions. And you can see the presence of corundum, quartz, and magnesite, but also pyrophyllite. And we observed that these inclusions, they have from 40 to 89% porosity. And in the case of Atabasca, the carbonates are predominant over the OH-bearing pyrophyllite. The second case study was the Ivrea Zone. So the rocks were a metapelitic, stromatic, metatic site, and also a diatic site from the Kinzigite Formation. The rocks contain different proportions, but the same mineralogy, so garnet, silimanite, biotite, feldspar, plagioclase quartz, with graphite as an important accessory, together with other accessories. And here the PT conditions are estimated in 850 and 900 degrees. And again, as you can see here, the garnet contains a cloudy aspect of the because of the high amount of inclusions that it contains. And again, we see this primary arrangement. When we look closer into these clusters, we see that there are two types of multiphase inclusions. The nanogranitoids, here are some examples. In this case, we see often the presence of graphite, also muscovite and chlorite in these inclusions. And then the fluid inclusions, they are also multiphase, and they have variable compositions and densities. So some have CO2-rich compositions, and others have methane-rich compositions, but always with traces of nitrogen. So the CO2 densities are also variable and below what's expected for the PT conditions of entrapment. So with the Raman maps and point analysis, we will observe that these inclusions contain several phases within them, several minerals, so siderite, pyrophyllite, but also kaolinite, graphite, magnesite, calcite, quartz, and corundum. And with the focused ion beam, we also did the serial sectioning. Here there's a video of the process where you can see the minerals and the cavity. And this technique permitted us to see that these inclusions contain from 33 to 48% porosity. And in some cases, the kaolinite is predominant, the OH-bearing phases, so kaolinite and pyrophyllite, they are predominant over the carbonates. The third occurrence was the Gruf Complex. Here, the macroscopic view of the rock that we studied. It contains a garnet, sapphirine orthopyroxene, cordierite, biotite, and K-feldspar. And the PT conditions are, it reaches higher temperatures, so 920 and 940 degrees. And again, the garnet has a primary arrangement of the inclusions. And in these clusters, we see not only the presence of nanogranitoids, where here there's an example of one of them, fluid inclusions, but also the presence of glass containing CO2 bubbles. So this is a very good evidence that these inclusions were trapped at high temperature and pressure conditions. So the fluid inclusions in this case, they have CO2-rich compositions and no traces of nitrogen or methane were found. And the densities, again, are variable and below what is expected for the PT condition of entrapment. So with the Raman, we observed that these inclusions contain magnesite, pyrophyllite, but also muscovite, biotite, siderite, calcite, quartz, and corundum. And with the serial section, we observed that they contain up to 24% porosity, and that the potassium-bearing phases, so muscovite and biotite, are actually abundant in this inclusion. So the original composition of the fluid may be evaluated just qualitatively by looking at the fluid phases and the minerals found within these inclusions, but a more precise and quantitative estimate can be done using the composition of the fluid bounded in the minerals within the inclusions. And we did this mass balance approach by considering the volume estimates that we did with the serial sectioning, so the 3D reconstructions, and the molar volume of the minerals from the literature to obtain the number of moles of carbonates and OH-bearing phases, and translate the composition into a binary composition in the CO2H2O system. So in Atabasca, when we look at the phases, we think we can say that this inclusion had COHN fluid, and as I already said, the fluid had a CO2-rich composition, but contained methane and nitrogen. And also the presence of pyrophyllite indicates that this fluid had also some H2O. A more quantitative estimate indicated an XCO2 of 0.95. The Ivrea case is more or less similar. We have a COHN fluid, but with considerable proportions of H2O, since we saw the presence of not only pyrophyllite, but also kaolinite. And the quantitative estimate indicated the XO2 between 0.55 and 0.7. The case of Gruf is a bit more complex because we have not only the fluid, but also the potassium-bearing phases. So we interpreted that the fluid was a CO2 H2O fluid, but it was kind of a mixed inclusion together with the silicate melt. So it was an intermediate member between the fluid and the melt. This kind of occurrence was also described in the alloy azo partially melted enclaves, where you have the fluid and the melt together. So the quantitative estimate indicated quite low XO2, but because of this influence of some minerals that are crystallizing from the melt, which are the muscovite and the biotite. Another intriguing point was to understand the origin of these multiphase fluid inclusions, because they're composed of solids and the fluid phase. So a possibility is that these minerals, they are actually trapped minerals, accidentally trapped. However, except for quartz and the biotite in the case of Gruf, these phases are not observed in the matrix of the rocks, and they are also incompatible with the PT conditions of entrapment. So this interpretation is highly improbable. Another possibility is that they represent daughter minerals, meaning that they precipitated directly from the fluid. However, at the PT conditions of entrapment, although solute can be dissolved into a COH fluid, the amount of solute cannot account for the amount of crystals that we observed in these inclusions. So this is also an unlikely possibility. What we do see is that the host garnet contains abundant amounts of the cations needed to form these inclusions. So there is a possibility that these minerals, they are stepdaughter minerals and result from the interaction of the fluid with the host. And in this case, the original composition must have changed and the density decreased by the reaction with the host. And in order to investigate this hypothesis further, we did phase equilibrium modeling with Perplex. We considered two systems involving a finite amount of fluid and garnet in excess. In the first system, we used a pure CO2 fluid, more or less similar to what is happening in Atabasca. And the second system with a binary fluid with the XO2 that we obtained for the inclusions in the Ivrea samples. So in the first system, we see that a pure CO2 fluid after entrapment, here represented by the star, this fluid and the host will start to react, the fluid will lose its density to form carbonate, kyanite, and quartz. We have not observed kyanite, but we have observed corundum and quartz, which is the metastable counterpart of aluminosilicates. And fluid inclusion studies and melt inclusion studies often report the presence of metastable phases in those tiny cavities, and metastability is indeed considered to rule in those inclusions. So when we consider a metastable system, we see that the fluid would form carbonate, corundum, and quartz. In the binary system, under equilibrium, again, we see that the fluid would react to form carbonate, kyanite, and quartz, but then very complex assemblages appear and they do not match our observations. When we consider metastability, however, we observe a sequence of assemblages that match much better the natural samples. So initially, after the entrapment, the binary fluid will react with the host. The CO2 is going to react to form carbonate, corundum, and quartz. The fluid will increase its activity in H2O, and then will react with corundum and quartz to form pyrophyllite. Then we will have an assemblage carbonate, corundum, and pyrophyllite. And finally, if this fluid has enough H2O, it will react pyrophyllite and corundum and H2O to form the kaolinite. So if you remember, here we have the inclusions of Atabasca, where you have carbonate corundum and quartz, or carbonate corundum pyrophyllite. And here the inclusions of Ivrea, where we have pyrophyllite and kaolinites together with the carbonates. So from these models, four conclusions are evident. Independently of the retrograde path, the garnet and the fluid will react to form these multiphase fluid inclusions. They are formed of a residual fluid and solids. The CO2 is the first component of the fluid to react with the host and form the carbonates, and the solid assemblage is metastable. And the starting H2O of the fluid will control the preservation of kyanite or corundum and quartz. So now another intriguing point is what is the origin of this fluid if it was present? And two possibilities can be envisaged. One is an internal origin for the CO2. This will be the case if the protolith was a graphite-bearing one. In this case, the CO2 can be produced by the volatilization reactions before amphibolite phases, but at granulite phases, it can be produced by oxidation of the carbon by the melting of iron 3 plus bearing biotite. And in this case, CO2 will be produced. It can partition to cordiorite, to the melt, but if you have enough fluid, it will form a fluid, a free fluid phase. And we think that for Atabasca and Ivrea, this is a likely possibility. As you can see here, the petrographic evidence of graphite in these rocks is very clear. And so this is a possibility in these two cases. Another possibility is an external origin for the CO2. So this can happen as a result of decarbonation reactions of other lithologies in the sequence, such as marbles, calc-silicates, but also as the carbonation of the mantle and the gassing of mantle-derived magmas. I have to emphasize that, so this is maybe a possibility for the Gruf complex, because in the samples from Gruf, we have not observed graphite. But I have to emphasize that the presence of carbonates in the fluid does not imply a mantle origin for the fluid. And the only way to pinpoint the origin of the fluid is by looking at isotopes, and we haven't done that. So these are just possibilities. So some implications of these results, the coexistence of primary melt and multiphase fluid inclusions, they indicate that anatexis occur in the presence of a COH fluid in a situation of fluid melt immiscibility. And the petrographic evidence and the phase equilibrium modeling suggest that these primary multiphase fluid inclusions, they are a result of the interaction of the fluid with the host garnet during cooling, and the assemblages within the inclusions, they are metastable. So this means that primary CO2-rich inclusions or COH fluid inclusions entrapped in peritectic garnet, they are prone to change their nature to a carbonate hydrous-bearing silicate assemblage as a natural consequence of cooling. So now maybe you can ask me, how can I reconcile this with those superdense monophase fluid inclusions described in the literature? Well, the simplest answer is that those inclusions may not be primary. And when we look at the petrographic evidence for their primary character, is that, to say the least, debatable. For example, here we only see high magnification pictures where we cannot identify primary or secondary arrangement of these inclusions. Some of them have irregular shapes that may suggest later entrapment. And as we saw in the beginning of this presentation, high-density CO2 inclusions, they can be trapped at low PT conditions. And this would be the only way that interaction between the host and the fluid would be inhibited as a consequence of the slowdown of kinetics at low temperature. So just the take-home message is then that these results, they challenge the classic view for the evidence of fluids in high-grade rocks, but we offer new insights to identify their presence. So only multiphase fluid inclusions in peritectic minerals, they are the true evidence of primary fluids operating at high-grade conditions. And these occurrences, they are far from being uncommon. If we look at the literature, we see that there are more than 20 case studies that have described or mentioned the presence of multiphase fluid inclusions in high temperature and ultra high temperature terrains. So with that, I leave you and thank you very much for your attention.
Thank you. That was very interesting. We've got one question from a student in the chat, so I'll read that out now. Maybe more will come through.
Okay.
This is from Anna Sapagina. Are there any evidence of halogens in the fluids?
No, I have studied many of these inclusions in all those rock types, and I haven't found any evidence for brines or anything like that.
So you have looked, but you haven't found it?
Yeah.
Okay, well, she says thank you.
Okay.
Oh, another student question. Is there evidence of decrepitation of fluid inclusions? I think I'm saying that correctly.
Yes, sometimes there are evidence for that, but because we wanted to avoid this, we did this study on the inclusions that are not decrepitated. So we believe that they contained the fluids were preserved within these inclusions.
Another question just popped up. How did you model the metastability?
In this case, we have just to exclude all the phases from the from the modeling, and then it will give you the metastable assemblage.
Okay, I assume. Oh, another question. Is there any evidence for these fluids causing melting? How can you tell the difference between fluids mixing with melt and fluids coming off the melt?
Yeah, the CO2 couldn't come from the melt because the amount of CO2 that partitions into these melts that are rheolitic in composition is quite low. So this fluid couldn't come from the melt. And yeah, the CO2 is present during the melting. Some is going to the melt. I have some data on those on the CO2 of the melt inclusions, but yeah, it's yeah. I don't know if I replied that actually.
Okay, another question. I have one, but I'm going to answer the ones that are popping up in the chat first.
Okay.
Some of your inclusions show really good negative crystal shapes, cubic or hexagonal. Do these show any specific characteristics?
Yes, they have. They may have negative crystal shapes, yes, but sometimes we see that in some places. Maybe I will try to go back. Maybe wait. I will back there in the video. We can see that some parts of the inclusion may not be exactly negative crystal, but kind of rounded. But more or less here you can see that it does have a regular shape, not an irregular shape such as the one that I showed by the end of the presentation. For example, they seem like tubes or, oh, sorry, I'm going to go there. So these, they are very irregular, so it's different. Okay, yeah.
Okay, another question. And we do have time now. The next talk is cancelled, so we can run a bit over. So from John Clemens, it sounds like most of the fluids were locally derived, particularly when you have graphite present. Do we have any evidence of external derivation of fluids driving reactions, rather than the fluids being local producers of reactions, products of reactions between the minerals?
Yeah, well, in this case studies, I don't have evidence for external fluids, and this sketch is a work that have investigated the carbon isotopes in the pylites and in the marbles, and in Ivrea, sorry, so in the sequence of Ivrea, and he hasn't seen any derivation from the other lithologies, so it's probable, again, some internal origin. And there's another paper that has investigated, because in the Ivrea Zone, there's the mafic complex close to the granulites. And so there was maybe a possibility that the fluid was coming from the mafic complex. However, this other study has also made an X in this one. It was not a possibility because the carbon isotopes, again, they don't show any alteration or changing that would indicate fluids coming from the mafic complex.
Okay, so I sold Peter Trelaw short. He was wishing to ask whether they had any distinctive fluid chemistries. So when he was asking about the inclusions that show negative crystal shapes. So do they have any specific or distinctive fluid chemistry?
No. Actually, no.
Okay.
Yeah.
Short answer?
Yeah, well, yes, it's a short answer. As I said, they have negative crystal shapes in some parts of the inclusion, in others they don't. And yeah, we haven't seen any kind of different chemistry according to the shape of the inclusions.
Okay, so I think we still have time. I was going to get onto mine, but other questions popped up. Hope we're not going to get onto mine. So a student question, have you tried to model the fluid as a solute-bearing fluid instead of a binary H2O CO2 fluid?
I haven't, and I'm not sure. I mean, maybe I'm wrong, but I don't know if that would be possible. It's quite complicated to put already the CO2 and, for example, yeah, I think it would be difficult. But if someone knows that is possible, I'll be happy to hear about that. Yeah, please write me on the comments later on so I can. Who asked that? Was a student?
Yes, it's Andrea Maffis.
Okay.
Might be saying that name wrong. I apologize.
Yeah, okay, it's no problem. So tomorrow he has a talk, so it will be interesting.
So Dick White has chipped in saying he thinks it's unlikely to have good thermodynamic data for the solutes of those high temperature pressure conditions. But
okay, so
maybe you can form a breakout room and argue about this. So my question was general. So I'm not a fluid inclusion person. I'm more of a cold subduction person. Why do you choose garnet to look for the fluid inclusions? Because there will be many peritectic minerals growing in the granulite fascies. But I always seem to see garnet focused on. Is there a reason for that?
Yeah, because the garnet it preserves more easily. I think because it forms embayments when it's growing. So it kind of preserves not only fluids, but also melt inclusions. But yes, when in the beginning of the talk where I talked about that we should look at peritectic phases, I didn't say that, but I wanted to mention that any peritectic phase would be a good idea. It's just that if we look at, we have to be sure first that the inclusions are primary. So if you have planar arrangements, I don't know, maybe it's not a good idea, even if the host is garnet, because for example, in some of those examples from the last slide, here the host is garnet, but yeah, we cannot be sure that those are actually secondary or primary. So even if we are looking at peritectic minerals, we still should be careful.
Okay. Mm-hmm. There are more questions, if you don't mind. So we're kind of going over here, but we can. Okay. So Dick has followed up with some more comments. It's fluid solute thermo that's probably the unknown rather than the fluid itself or the minerals. It's fine. Claire Warren has asked, is there any way of estimating the volume of trapped fluid trapped compared to not trapped? Do you think there's any way to estimate this? How much the proportion of fluid that becomes trapped?
I don't know. I don't think it. I think it would be extremely hard to estimate how much you can trap. I have to think about that. I don't know. But again, if there are any developments on this thought, I'm open. Claire, please.
Bernardo has said in the chat that one inclusion was found in Asafarine, but one is not a statistically significant population size, which I agree with, obviously. Okay, the questions might have petered out there, so I'll give you a break.
Thanks.
Oh, sorry. Owen Wells got one more.
Okay.
So let's make this the last question, and then we can have 10 minutes before the next talk. Owen says, is there any evidence for core to rim zonation in fluid X CO2?
Actually, well, we have seen the changes in composition of the fluid in the same garnet, but not as a proper zoning, something regular. I don't think so.